Hello students, welcome to EPG Pathshala. I am Dr. Shashank Deep from IIT Delhi. I am Associate Professor in the Department of Chemistry of IIT Delhi. Today we are going to talk on module binding of two different ligands. This is the module from paper Biomolecular Interactions. So students, let us see what we are going to learn in this module. First we will start with introduction, then we will discuss protein ligand binding equilibria. There is concept of macroscopic constant and microscopic constant. We will learn what do we mean by macroscopic and microscopic constant. Then, as we done in the previous module, we will see how to calculate fractional saturation of a site for a protein with multiple sites. We will again look at the sketch chart plot. We will start with multiple independent sites for the same ligand but with same affinity. Then we will like to see how this plot changes when we have multiple independent sites for same ligand but with different affinity. Then finally we will go to cooperativity, where the sites are dependent, means there is interaction between sites. If there is interaction between sites, we have a cooperativity, and there is a relationship which gives you how a sketch chart plot look like in terms of Hill constant. And then finally we move to allosteric protein, and we will look at two very important binding models. One is called concerted model given by MONOD-WYMAN-CHANGEUX MWC model, and the second one is sequential model, which is also known as KNF model. More often, binding to ligand is not simple 1:1. There can be multiple ligand binding to one single protein, or there are different binding sites for a same ligand. So, many biological processes involve binding of ligand receptor to more than one receptor or ligand. Examples are also known in which multiple sites exist for same ligand. For example, binding of oxygen to hemoglobin. Sometimes binding affinity of ligand depends on fractional occupation of the site. Examples are also known in which multiple sites exist for the same ligand. If binding affinity for ligand increases with increase in fractional saturation, that is called positive cooperativity. On the other hand, if it decreases, then it is called negative cooperativity. Concept of macroscopic constant. So let's understand the difference between the two constants, macroscopic and microscopic. What do we mean by that? So if we start with glycine, we know that it has 2 pK value. What does that mean? That it is a dibasic acid, and it has 2 titrable binding sites. The sites are GH2 plus going to GH plus H plus, and then GH giving you G minus plus H plus. So we can think of 2 macroscopic constant, where K1 is given by GH into H plus divided by GH2 plus, while K2 is equal to G minus into H plus divided by GH. So this is the simple concept of macroscopic. We are just considering dissociation of one H from GH2 plus. Which H? Concept of microscopic constant. So the things which I told you, that GH exists in, or glycine exists in 2 forms, And so there are 4 species, not simply 2 species. And therefore, if we go on the microscopic level, we can think of 4 different equilibrium constants in place of 2 constants when we are just considering macroscopic constant. So your Hg can exist in 2 different forms. One in which you have H has taken out from your carboxylic side. So it has negative charge, and that is compensated by 1H plus at NH2 end. This we tell as Hg form of the glycine. While the second proton, titrable proton, can be from NH2 side. And when that is dissociated to get GH form, that is NH2 CH2COH, and that's what we call as GH. In that case, we can think of 4 different equilibria. Initially, we have at the acidic pH, your GH exists as NH3 plus CH2COH. Now it can dissociate in 2 different ways. First, when carboxylic acid is lost. In that case, we will get NH3 plus CH2CO minus, and for this step, we consider microscopic constant as K1. There is another possibility that H can be lost from NH2 group, and in that case, we will get NH2 CH2COH, and the microscopic dissociation constant in that case is suppose K2. Now, both this form, Hg and GH form, can further dissociate to give you NH2 CH2CO minus. When Hg goes to G form, the equilibrium constant is K3, and when GH goes to G form, equilibrium constant is K4. How we can correlate the macroscopic constant with microscopic. So macroscopic constant is nothing but your GH into H plus divided by GH2 plus. Now since GH can exist in 2 forms, GH or Hg, we can simply write GH plus Hg multiplied H plus divided by GH2 plus. So this is equal to K1, and that is simply equal to K1 plus K2. Similarly, K2 can be expressed as 1 divided by K3 inverse plus K4 inverse. So this is a simple relationship between your macroscopic and microscopic constant. There is also a relationship between microscopic constant. If we solve it, we can simply get K1 into K3 is equal to K2 into K4. Now, when there are more than one sites, we can go and calculate fractional saturation as we have done in the earlier module. In this case, what we are going to consider is equilibrium when a ligand binds to a free site to give a bound S. S is site, it can exist as a free site or bound site, so S plus L giving you SL. SL is simply bound S. In that case, microscopic constant K is given by S into L divided by SL, and so SL is given by S into L by K. So fraction of bound protein is simply SL divided by S, free S plus bound S, and that is simply L by K divided by 1 plus L by K. So fractional saturation of a particular site can be calculated using this equation. We try to see which kind of a sketchart plot we can get for protein with multiple independent sites for the same ligand with same affinity. It is simple, the sum of we can treat as 1:1 interaction and simply multiplied by n, which is number of ligand on a site. So nu is equal to simply given by n multiplied by L by K divided by 1 plus L by K. So nu by L is equal to n by K minus nu by K. Again, when we plot nu by L, versus nu will get a straight line with slope equal to minus 1 by k and intercept equal to n by k. By slope, using slope and intercept, we can calculate number of ligand binding to a particular site, and we can also calculate microscopic constant. If suppose we are looking for a protein with multiple independent sites for the same ligand but with different affinity, in that case we can simply write nu is equal to, which is the fraction of bound protein, is sigma ni by ki divided by 1 plus L by k, and this is summation for all the independent sites. In that case, nu by L versus nu will not be a straight line, it will be curved with your intercept on x-axis given by n1 plus n2, while intercept on y-axis will be given by n1 by k1 plus n2 by k2. Till now we have discussed multiple independent sites for the same ligand. Till now we have talked about independent sites. There are cases when there is interaction between sites, which is known as cooperativity. What do we mean by interaction between sites? Is basically when binding of one ligand to one site affects the binding affinity of the successive ligands. So binding at one site affects the binding at another. In that case, your sketch chart plot nu by L versus nu will not be linear, it will be concave up if K increases as saturation proceeds. What does that mean? That successive ligands bond weakly. And the curve will be concave down as binding proceeds, successive ligands are bound very strongly. So there are two different cases when there is interaction between sites. Hill's constant. So if suppose our ligand binding is highly cooperative, what does that mean is protein binds exactly in molecules at a time or binds none. So protein exists as either PLN or simply protein. So this is called all or none reactions, and this is the extreme case of infinite cooperativity. So let's calculate fraction of bound protein in case of cooperative systems. The way we calculate fraction of bound protein is given here. So you can see the equation which tells you about binding all or none reaction can be expressed in one single equation, P plus NL going to PLN. So in that case, Kn will be given by P into Ln divided by PLN, and fraction of bound protein can be calculated using nu is equal to N into PLN divided by P in free form plus P in bond form. There is only one bond form, that is PLN. And then we can express nu is equal to N L power N by Kn, 1 plus L N divided by Kn. So simple equation in nu by N is Ln by Kn divided by 1 plus Ln by Kn. Binding may not be fully cooperative. In that case, fraction of bound protein is denoted as L by K power alpha H. Well, alpha H is Hill coefficient. Denominator you get 1 plus L alpha H divided by KH. So alpha H is known as Hill constant, and that is used to describe cooperativity. If Y follows this equation and alpha H is equal to N, then we say binding is fully cooperative, but if alpha is equal to 1, then we say binding has no cooperativity. So Hill constant is used to define cooperative system. If alpha H Hill constant is equal to number of binding sites, we see that the system is fully cooperative. When alpha is equal to 1, then we say binding has no cooperativity. So this shows you the plot between fraction of bond protein versus L divided by K. You can see that when alpha H, this is for protein with binding site is equal to 4 independent binding sites. In that case, if we take alpha H is equal to 1, then you can see that this is a hyperbolic curve. As alpha increases, the curve moves from hyperbolic to sigmoidal. So a sigmoidal kind of curve, a plot between fraction and L by K, tells you that system is fully cooperative. Let us now look at allosteric protein, binding models for allosteric protein. So first let's know what is allosteric proteins. Allosteric proteins are proteins which have sites other than catalytic sites, which are specific for physiological molecules that regulate the protein activity. Generally, when we know a protein is allosteric, just by looking at kinetics. Allosteric proteins show sigmoidal reaction kinetics in place of hyperbolic reaction kinetics shown by simple proteins. There are some of the well-known examples of this protein. First is your aspartate transcarbamylase, which is also known as ATCase, and your hemoglobin. There are two different kind of models which are generally used to explain your cooperativity in allosteric proteins. First is what is known as concerted model or MONOD-WYMAN-CHANGEUX MWC model. This model has several assumptions. First one is proteins have several units and each unit contains one binding site for each specific ligand. Each unit now occupies equivalent position in the protein. Protein can undergo conformational change, and change is between two states. One is called relaxed, the second one is known as tense or tau. The affinity of ligand for a site is different in two states, means relaxed and tense state. Ligand binding affinity doesn't change with occupancy of the neighboring site, so K is not changing. So going to discuss allosteric proteins and the way the binding in allosteric protein is explained is through two different models. One is MONOD-WYMAN-CHANGEUX model, which is known as MWC model. In this, protein can exist in taut form. You can see there are 4 domains, 4 sites for protein, and all sites in the left figure is in the tense form or taut form. The middle one is the protein when protein sites are in relaxed form. So all 4 forms are in all 4 sites are in relaxed form. MWC doesn't allow for the mixed state. What does that mean is that 3 of the sites are in taut form and 1 in relaxed is not allowed. Either all 4 forms are in tense form or all 4 forms are in relaxed form. Now let's see how we can calculate fraction of bond protein in case of MWC model. So let's denote R0 as F1, F2, F3, F4. F represents free sites. So there are 4 sites on the protein. Suppose there are 4 sites, then we can show R0 as F1, F2, F3 and F4 and RL as one site occupied by a ligand, and that site is called B. Then RL can come from 4 different ways. RL can be made from 4 different forms of protein, that is B, F2, F3, F4. In this, the first site is occupied by ligand. then plus F1B, F3, F4 where second site is occupied, F1, F2B, F4 where third site is occupied by ligand, F1, F2B, F4 where fourth site is occupied by the ligand. Now Kr is simply anything you can take. First form simply F1, F2, F3, F4 when it binds to one ligand, that is equal to Kr. The second ligand, similarly you can write another equation for the second binding. For each successive binding, Kr is constant in the MWC model. So 1 by Kr is simply equal to Bf2, F3, F4 by F1, F2, F3, F4 into L. So 4 by Kr is simply equal to all the 4 conformations in which one site is occupied by ligand divided by the free protein into L, and that is simply RL by R naught into L. So RL can be denoted as 4 R naught alpha, where alpha is L by Kr. So RL can be expressed as 4 R naught alpha. Now take second binding. Second binding can happen in 6 different ways. And first 2 sites are occupied, and first and third site is occupied, and first and fourth site is occupied, when second and third site is occupied, when second and fourth site is occupied, and when last 2 sites are occupied. Then RL2 can be written like 3 by 2 RL alpha. Similarly, we can do for the third binding. In that case, 3 Kr by 2 is equal to RL2 by L by RL3, and for the fourth binding we can write 4 Kr is equal to RL3 by L RL4. Now we can express RL, RL2, RL3 and RL4 in terms of R and alpha, and simple equation which we get is RL is equal to 4R alpha, RL2 is equal to 6R alpha square, RL3 is equal to 4R alpha cube, and RL4 is equal to R into alpha 4. If suppose binding is to the tense form. Similar kind of equations which we did with the relaxed form, we can also do for the tense form, where TL is equal to 4T into beta. Now you see, we just converted alpha into beta. Beta here is given by L by KT, where K is the dissociation constant with the tense form. So TL can be written as TL, the 4T beta, TL2 can be written as 6T beta square, TL3 is written as 4T beta cube, TL4 is T into beta 4. If suppose Kr by Kt is equal to S and C is T by R, then we can write beta as S into alpha. Then in that, if we do that, we can express TL, TL2, TL3 and TL4 in terms of your concentration of relaxed form, S, alpha and C. And these are the 4 equations which can give you TL by TL2, TL, TL2, TL3 and TL4. So equilibrium fractional saturation is given by your Y is equal to the sites which has been occupied divided by total number of sites. So in case of RL, only one site is occupied. In RL2, 2 sites is occupied. In RL3, 3 sites is occupied. R4, 4 sites is occupied. So total number of sites occupied is given by 1 into RL plus 2 into RL2 plus 3 into RL3 plus 4 into RL4. As similarly on the tens form, we can simply write 1 into TL plus 2 into TL2 plus 3 into TL3 into 4 into TL4. When we calculate the total number of binding sites, each form has 4 binding sites. So we simply multiply this by 4. So 4 into R plus RL plus RL2 plus RL4 plus T plus TL, TL2, TL3, TL4. When you calculate the first part, 1 into RL plus 2 into RL2 plus 3 into RL3 plus 4 into RL4 by equation which we derive for RL, RL2, RL3 and RL4, we simply get 4R alpha 1 plus alpha q. Similarly, we can calculate for 1 into TL plus 2 into TL2 plus 3 into TL3 plus 4 into TL4 is simply equal to CR S alpha 1 plus S alpha q. We can calculate total concentration of R, RL, RL2, RL3, RL4, that is simply equal to R into 1 plus alpha 4, and similarly we can calculate T plus TL plus TL2 plus TL3 TL4, that is simply equal to CR1 plus S alpha. So now we can calculate Y with the fractional saturation is simply equal to, since 4 cancels out from the denominator and numerator, you are left with alpha 1 plus alpha q plus CS alpha 1 plus S alpha q divided by 1 plus alpha 4 plus C 1 plus S alpha 4. Now if we suppose there is n binding site in place of 4 binding site, then we can simply write this equation as Y is equal to, we replace 3 by n minus 1 and 4 by n, so we have simply left with alpha 1 plus alpha n minus 1 plus CS alpha 1 plus S alpha n minus 1 divided by 1 plus alpha n plus C 1 plus S alpha n. Suppose F binds strongly to relaxed state, what does that mean? That simply means alpha is less than 1. And if we suppose this enzyme starts out largely in T state but ligands binds exclusively to R state, that means S is equal to 0 and C is quite greater than 1. So C quite greater than 1 means we start largely in the T state and S is equal to 0 means ligands binds exclusively to the R state. In that case, our equation simply comes out to be 1 plus Y is equal to alpha 1 plus alpha n minus 1 divided by 1 plus alpha n plus C. Now let's see which kind of graph we will get when we plot Y versus alpha. Suppose alpha is very low, it means ligand we have added is in a small quantity. In that case, simply 1 plus alpha is equal to 1 and then we can simply write Y is equal to alpha divided by C. This is simple, that YF increases linearly with alpha but with a slope 1 by C, and that's we see in the initial region. Now suppose 1 is equal to alpha is quite less than C, then YF is alpha by C plus 3 alpha square by C plus 3 alpha cube by C plus alpha 4 by C. So when alpha is greater or it is almost equal to 1 but is still quite less than C, then YF begins to change rapidly in response to a small change in C. That's what we can see in the curve. Initially there is very small change and then there is a very rapid change, and that's how we get a sigmoidal curve. Shows you the effect of C, which is the conformational constant, equilibrium constant on the plot, that is the left plot, and then effect of changing S, which tells you about the binding with relaxed state. So if we increase C, we can see that for C is equal to 1, we have the plot is a hyperbolic one. What does that mean is when tense and relaxed form, we start with a state, when tense and relaxed form are equal, then you have a hyperbolic curve. But when you start from C is equal to, if you go C very high, means most of the protein are in the tense form, then you can get a sigmoidal kind of curve. Right hand side plot, S basically tells you about the binding dissociation constant. So if binding is only with the relaxed state, then you get a sigmoidal curve. That will happen when S is equal to 0, and if you go S is equal to 0.1. This means that ligand also binds to tense form. In that case, you can get a hyperbolic curve. Tells you about effect of activators and inhibitors. This model assumes that activator binds to R state and inhibitor binds to the T state. These binding sites are different from the catalytic binding site. Allosteric effectors modify the apparent equilibrium constant for the T to R transition, and the equation is given by this. L apparent is equal to L 1 plus I by KTI, where KTI is equilibrium constant from T to I form, and KRI is equal to equilibrium constant from R to I form. The second binding model which we come across is known as KNF model or sequential model. In this model, intermediate conformation are possible. So all the sites are not only in the tense or relaxed state. There is a possibility that some site is in relaxed state and others are in tense state. There is unique microscopic dissociation constant for each ligand binding site. So dissociation constant changes for successive ligand. Respective dissociation constant may increase or decrease. If it increases, that is positive cooperativity. When it decreases, then there is negative cooperativity. Thus can account for anti-cooperativity, which is not possible in concerted model or MONOD-WYMAN model. This is KNF model. This is another model used to describe allosteric protein binding in allosteric protein. In this case, intermediate conformation can also exist. It means out of 4 sites, 1 can exist in relaxed form, whereas 3 can exist in tense form, which is not possible in MWC model. Extreme case of KNF model is when a ligand binds to one of the sites, all 3 other sites undergoes conformational change, and then second ligand binds to another site, the 2 free sites again undergoes conformational change. So the lower picture denotes the extreme case of cooperativity, and if you calculate the fraction of bond protein, it is given by Sn divided by K dash into Sn. This is a typical scenario with the Hill constant also, where n is equal to Hill constant. So students, let us now summarize what we have learned in this module. First, a ligand may bind to one or more sites. Similarly, more than one ligand can bind to a protein. Binding of one site can affect the binding of ligand on the other side. Dissociation constant of the individual binding steps are called macroscopic dissociation constant, whereas dissociation constant of binding to individual sites of the macromolecule are called microscopic binding constant small k. If there are multiple independent sites for a ligand with same affinity, SK chart plot is linear. And we can calculate number of binding sites and microscopic constant if we know the slope and intercept of SK chart plot. However, if there are multiple independent sites for a ligand with different affinity, then SK chart plot is going to be curved rather than being linear. So just by looking at SK chart plot, you can make a guess about type of sites present for a ligand. If binding of one ligand to one site affects the binding of successive ligands, again SK chart plot might again be curved. For allosteric protein, the SK chart plot is sigmoidal. So if you look at sigmoidal curve, it means allosteric proteins are present and cooperativity is there. There are 2 important binding models, MWC model, KNF model. KNF model can account for your anti-cooperativity. In MWC model, protein exists either in tense or relaxed state, whereas we cannot think of intermediate conformation. While in KNF model, not only tense and relaxed state is available, there are intermediate conformation also present. Thank you.